It's really a great honor and pleasure to welcome here Patrick Peréz, who just came in from Paris. Patrick is a VP at Valeo, or VP of AI at Valeo, and the scientific director of Valeo.ai, which is an AI research lab focused on automotive applications and self-driving cars in particular. So before joining Valeo, Patrick was a researcher at Technicolor, Microsoft Research Cambridge, and INRIA. Patrick is very well known for his work on multimodal scene understanding and computational imaging. And it's an honor and pleasure to have Patrick here. Patrick, welcome, and the floor is yours. Thank you.
Thank you, Josef. Thanks for the invitation. Always great to be here in Prague. So, given the temperature, I should have talked about reinforcement learning for thermal comfort management, so something we do for in-cabin vehicles. But the topic is different today. It's about autonomous cars. And in particular, where are they? I mean, they have been promised in 2015, they have been promised in 2018, 2020, etc. And somehow they're not yet here. So today, I'd just like to say a few things about the state of affairs, also with illustrations from, with research from my team. But of course, it started as a dream. This is an artist depiction from the mid-50s in a commercial. Actually, it's quite interesting. It's not so far from what new artists are envisaging. But anyway, so that was the dream. And to some extent, the dream almost came true already quite a while ago. I don't think it's very well known, even in Europe. It's a shame, because from the mid-80s to the mid-90s, there was a funded project, in particular with France and Germany, called Prometheus. And it was about autonomous vehicles. And what you see here is that with the technology of the time and the compute of the time, they managed to have first this big van, the Mercedes van, and then an actual passenger car equipped such in a way that it could be driven autonomously on the highway with lane changing using, guess what, a camera with a neural network. So that was pretty amazing. And I have put the link to a complete video on YouTube if you want to check out. It's very interesting. Of course, there are other milestones. In particular, on the other side of the ocean, there were these two well-known DARPA challenges in the US about autonomous vehicles, one in 2004 in the desert, and the other one in 2007 in sort of fake urban environments. And that was a big boost also to the topic. And not long after, we saw that already this morning, the little car from Google, so the Google car, which was the inception of the modern era of autonomous vehicles. And effectively, they are becoming a reality. For people who are going to San Francisco, for instance, in particular, Waymo, which is the former Google car branch, so it's an Alphabet division, as well as Cruise, they are now allowed to deploy 24 hours a day, every day, actual robotaxi services in town. So things are getting very, very tangible here, and the same in China with Baidu, for instance, so things are actually moving forward. But so this is quite spectacular, but at the same time, it shouldn't hide a very important fact that when it comes to autonomous vehicles, we are talking about many different types of vehicles and many different types of use cases. Let's start with delivery. So this is a big topic, delivering. This is also sometimes called the last mile delivery problem, with small vehicles which don't run very fast, and they are packed with goods. You can do the same with people, with shuttles. They go from A to B to A, not very fast, and they are very useful. You see here two French startups. Unfortunately, the first one has recently closed down. But also, it was also alluded to this morning, there is other probably less well-known things. At the bottom, you see these big, these monsters from the mining or the industry or the agriculture. And on the top, you see another branch of Waymo, which is about logistics and trucks. So lot is happening. Now, when it comes to passenger cars, which is what people have in mind when we talk about autonomous driving and autonomous cars or driverless cars, it's a bit more, well, complicated. So we have, I'm not going to explain in detail this table here, but this is the sort of official terminology or ranking of the different levels of automation when it comes to driving. On the left, the blue part is level 0 to 2. It's assistance, so the driver is in charge. On the right, mostly green, it becomes partial or less partial automation, and it goes from level 3 to 5, and in this case, the system, when engaged, is in charge, okay? When you think of this classification here, it means that typically the robotaxis are here because there is no driver at all, but they cannot go everywhere. They are geofenced. So essentially, it's a level 4 automation. But if we think in terms of passenger cars in particular, which are actually commercialized, well, there are a few well-known brands, American, Asian, or Europeans, which do that, level 2, level 2 plus, for instance. In particular, level 2 plus, there is a Mercedes car which was released last year. They doing what is called traffic jam assist on the highway, less than 60 kilometers per hour, but in this case, the driver can really do something else. It turns out that in case of problem, he needs to be able, or she needs to be able to recover, to take over within 10 seconds, which is quite demanding, but at least you can do something else and get your eyes off the road and your hands off the steering wheel. Level 3, well, I mixed up a bit. What I just described is actually level 3, but it's very limited in terms of speed and type of domain of operation. And as far as I know, there is not more in terms of passenger cars, at least commercially speaking. So maybe it's important at this stage to stop here, but to understand why we care, why we pour so much money and energy and research in either autonomous driving, which is sort of one of the holy grails, but not the only one. The other one being what is called ADAS, for Advanced Driving Assistance Systems, that we have in passenger cars nowadays. The obvious first reason is safety, in order to reduce the casualties on road, and there are still too many of them in the world, but not only, and also it was alluded to some extent this morning with robots. There are other benefits. One is, of course, to free the time of the driver, so more comfortable, but also to make things more cost-effective when it comes to robotaxis or logistics. By the way, there is a strong shortage of truck drivers in Europe. It's also more inclusive in the sense that for people who are deprived of the ability of driving, maybe now they can, again, get the ability to move around with these vehicles. All in all, it should allow to have a smoother traffic, being more efficient, and hopefully more sustainable for these reasons. So plenty of motivations to work on that, and as a researcher, there is also the motivation that it's super hard, so it's very exciting. So, which brings me to the challenges in a nutshell. One have to bear in mind that these systems, whether autonomous driving or driving assistance, well, first of all, they are embedded in a vehicle, so it's essentially an autonomous robot. Everything has to run in real time or super real time with limited resources. But of course, it's highly critical in terms of security. You cannot mess around with these things. It's deployed in the wild in very complex environments. And once in the road, these vehicles, they are there for 10, 15, 20 years. It's not like a mobile phone. And one of the important things is that it's a lot based on machine learning, which is great, but comes with well-known limitations. So at the end of the day, in order to have these things put on the road in a trustworthy manner, you need to make sure that they're actually reliable in a broad sense, that they are thoroughly validated, which is something we do at Valeo actually in Prague, and that they are certified as any vehicles on roads. Let me go through rapidly the typical driving stacks, which is effectively, again, at least in this classic version, an autonomous robot stack. You start with one or several sensors whose signals are fused either late or early in the system in order to build some perception of the world, and it might or it might not be combined with precise geolocalization and the accessibility to a HD map. It's not mandatory, but all these things put together allows the ego vehicle to build a model of the scene around it, up to probably, like, say, 200 meters away. And based on that, then you start predicting or forecasting the trajectory of the other road agents, and this is fed to the planner and then to the actual control of your vehicle in terms of direction and speed. If you think now of what has happened with the revolution of deep learning a decade ago, well, essentially deep learning has started to sort of to enter this stack, in particular, not surprisingly, for perception, but also for prediction, a bit less for planning, to be honest. But there is another route, which was again mentioned this morning for robots, which is way more radical, which is called end-to-end driving, where you try to learn to design and learn a monolithic model which goes directly from raw sensing directly to action. And there are actual systems on the roads doing that. In particular, you can check out the Wave startup in England. Okay, let me show you something that we do at Valeo, already an old video, but I think it's interesting. It's one of our experimental platforms for autonomous driving. You might recognize at the bottom Paris, so it's driving in Paris in this case. Also long-distance driving at the top with different trips that we've made. What is interesting, I just highlighted it, is that this platform, it's not a real, well, it's a real car, obviously, but there is a lot of things in the trunk, like compute. But the sensors, the actual Valeo sensors that we build and sell for the car makers. I will say something more later, but just playing the video, you will see that this vehicle is able to, handle the Parisian life, which is not always very easy or quiet, as Josef knows. You see the inside of the car. You see also the technical view with some 3D detection with boxes, etc. And also, of course, you should be able to go from light to night or to tunnel, etc. And this is one aspect of robustness that I was alluding to, and that's why I stopped my excerpts on the low light conditions for 3 of them. In terms of tasks, well, I will talk now mostly about perception. So there are a bunch of them. These are just examples from different labs. In this case, it's ours, where it's Valeo in the US, working on the. So it's the typical 2D perception task. Everything is in the image domain. In this case, it's the analysis of the detailed analysis of the pedestrians, including the pose and the intention to cross or not, which is obviously very, very important. Or whether the pedestrian is aware of the coming car, something that we do a lot with eye contact with human drivers. Not always. Another example, which is now still in the image domain, but 3D. Oops, didn't play. That's funny. Okay, doesn't matter. So this is actually annotation from the Waymo open data set, where you see the boxes in 3D for the objects in the scene. But this is still image-based. But then you can also do perception with the laser scanners. They're called LIDARs. In this case, you see, again, 3D boxes. These are annotations. These are not the results of actual systems. And it's from the very good new scene data set. But now moving to more complex tasks, you can do what is called 3D semantic occupancy, which is a fairly recent task, where in this case, just from the feed of your 6 surround cameras, you want to infer a sort of volumic understanding of the scene around the car. So what is empty, what is full, and you probably see the point. And it's not only whether it's full or empty, but also what is the nature of the object. So what you see at the bottom on the left is colored with the actual semantic, and on the right is only for the color. The coloring is only for the road users. And this is actually taken from an upcoming CVPR workshop this summer, which is called 3D Occupancy Challenge. And also this looking around the car, there is yet another task, which is motion forecasting. I already mentioned that in the driving stack, and this is work from the University of Cambridge. In this case, so first of all, it's what is called a top view or bird eye view perception. So everything is sort of inferred in the in a top view around the ego car. And the task here is to be able to predict in the future what is the likely position of each of the vehicles. And on the right, you see as well that it's very brief, especially when there is an intersection. This forecasting should be multimodal, because at some point in time, for some of the situations, there is a few likely outcomes of the future, whether the car in front is going to turn or not. And you see briefly here that let's see, you have some spanning of the hypothesis here. So it's one of the challenges in machine learning, which is to predict multiple outputs, in particular when in the training data there is not such thing because there is a single feature. Now that we have illustrated these different typical perception tasks which are involved in driving assistance and automation, let's come back to some of the challenges. So one of the big challenges is the fact that, especially for passenger cars, is the diversity of the conditions in which the system is deployed. So there are different so-called domains, and in terms of machine learning, it means different types of input distributions. There are rare events, perturbations. So I'm just showing examples here. So here, these are different conditions, either due to the different lighting condition or weather. So on the left, you see rain at night. In the middle, you see heavy fog. It's hard in the distance to know whether there is an actual obstacle of some sort. It's so heavy. On the right, you see also different types of conditions which are associated to different locations in the world, different types or styles of driving. And obviously, it contributes to the complexity and to the challenge of the robustness and reliability of these systems. Other examples, which are more related to perturbations which are maybe transient. You are still in your zone of comfort. You are driving, you know how to drive on the highway in the Silicon Valley, but unfortunately, it's still difficult only, just with cameras not to be blinded by the sun glare. This is the example you see with an actual Tesla car having difficulty because of the sun glare, and you see that the driver is struggling a bit to counter the decision of the car. What you see on the right, top right, is another example where when you have your cameras quite low mounted on the car and externally, then they get soiled. And this is the typical kind of things you get, and obviously the perception is not good. And at the bottom, what I was illustrating are sort of corner cases or rare instances of things. I mean, as humans, we understand that right away. We see, a bike at the back of a car. We see a truck with cars, or we see a guy, unfortunately, falling down, a cyclist on the pedestrian crossing. I mean, it's not very hard to decipher, but it's very rare from the machine learning perspective. One way to sort of attack all these challenges, it's not the only way, but one way which is quite widespread is to use multiple types of sensors. They have complementary properties. In particular, this is the typical here, what you see, the typical suite of sensors that you can put on a car. The ultrasonic sensors, which are for really near-field parking functions. They do beep-beep when you reverse. You can have also radars at different ranges. Obviously, cameras. We love that. Computer vision people. They can be fisheye cameras, pinhole cameras, and also we have these laser scanners that are very, very useful. I already showed cameras and point clouds in my previous slides about typical tasks involved in perception. I just wanted to show another one which we love in my team, which is radar. So radar, it is interesting, not because it's easy to read, at least for the human eye, but because it has very interesting information here. You see, so radar signal is essentially a big 3D tensor or volume of energy that is sort of showed here into different planes. It essentially tells you what is the reflection at a given distance in a given direction. and it also gives you the relative speed of the object. And if you have annotated data, which we have done and released a data set about, then you can, out of this quite complex signal, you can train essentially a neural network which looks at these different 2D views of the 3D input tensor. In that case, it was a convolutional network which was trained in order to actually precisely segment what are the road users. This is what you see on the right in 2 views. Actually, the green blob is an actual cyclist, and the red one is a pedestrian. So, and I forgot to say that when I mentioned complementarity, the radar is really achieves whatever the weather condition, which is not so true for LiDAR. They can be obfuscated by heavy rain or fog, etc. But they are quite robust. And the camera, which is fantastic to read things, to understand everything, unless you don't see anymore. So they have obvious complementarities. All right. Another topic which I find is I think is very promising. Many of you have heard about self-supervised learning. Actually, it's a big thing when it comes to these large language models that everyone is aware of. So the ability to learn from data without any human annotation. Well, it's something which is quite and very useful when it comes to also to driving automation. So we have been exploring in my team several aspects. So I'm not going to explain too much these 2 works. Actually, the one on the right already appeared on the slide of Josef this morning. It's the work of Antonin, who is at the back there of the room, sweating. And the idea here is that because you can leverage when you have several sensors, at least at train time, you can leverage the fact that there are lines. So you have a point cloud from the LiDAR, you have the images from the cameras, and you can geometrically register them, and you can pass from one modality to another some information and distill knowledge, and even build what are called pretext tasks to learn automatically representation out of these 2 modalities without any annotation. And then later you can specialize that with some training, some supervision, sorry, or not, for in this case for point cloud or image semantic segmentation. I have 2 more examples of this same thing. So this is a follow-up work of Antonin and Josef and colleagues at Valeo.ai, where effectively what we leverage here is actually not only LiDAR and cameras, but also what comes with language. So now you have, these days you have these off-the-shelf, extremely powerful so-called visual language models, which have been trained such that you can essentially map both images and text in the same the same abstract yet numerical space where things close together are related. And so in this work, we actually, but we don't have that for point clouds. So the idea here is to go to leverage these text and image representations and to distill them in 3D. In the point cloud, and in this case we did that while designing a model to actually deliver the following task, which is, I already mentioned it, which is 3D semantic occupancy. And you see on the right some examples of what you can do. So at the end of the day, from the cameras, you end up with an actual 3D volume around the car, and for each cell of this volume, you have some what we call features or representations, which are essentially vectors. And these vectors are very rich, and in particular, they also contain, so they do contain information about whether the voxel is empty or not, but also what is the semantics of the voxel. So which this allows to do what is called, well, that's good then, what we call a zero-shot semantic segmentation. So you can just say, I want to see all these classes, and just look at these features without any further training, and you get some decent segmentation. Thanks to the same property, which is the sort of knowledge embedded in the 3D features from this image text align model, we can also search directly by prompting. Look in this scene. Look for I think in this case it was a zebra crossing, and it just pops up out of the 3D grid without any training. And we have another sort of parallel work in my team, which was actually doing a similar thing, but sort of the other way around. The idea here is to be able, in the previous work that I just showed, is to use only at runtime cameras. In this case, we use the LiDAR, and we are able to distill these very rich image text features onto the point cloud, such that we can directly analyze the point cloud of a LiDAR, an automotive LiDAR here. And in this case, you see sort of a heat mapping on the point cloud related to some classes. So in particular on the right, it's pedestrians. On another example here, cars on the left or pole on the right. And again, it pops up without any specific training. Of course, the people who train the large image text models, they have trained a lot, and they have been doing that at large scale. So we leverage what they did. Another important things that people don't necessarily realize is that machine learning can be deliver very strong performance, but a neural network is not very good at assessing itself in terms of confidence or uncertainty. And being able to do that in a good way is very important to train better models, but also to validate them, and of course, at the end of the day, to have more reliable systems on roads. And again, it's difficult because it's well known that it's hard to know what, for the network to know what it doesn't know. And also, the output can be very wrong and very confident at the same time. So one illustration of that, which is fairly well known, is that you can, which is called an adversarial attack. You can take a very good system, able to recognize the panda here, and you can work out a very subtle modification which is not visible to the naked eye, and the same system tells you, oh, now it's a gibbon, and being as confident, like 90% confidence. So it's a bit scary when you put that in a car. So people used to say that deep learning or neural networks are brittle. Well, it's one aspect of it. So one of the things that we have been exploring in my team and other people as well is to have a sort of a safety or a guardrail, which is another model on top of it, which observes the main model. So in this case, at train time, you have the auxiliary model. So in this case, say you have this task of semantic segmentation in images. So the main model predict a semantic label at each pixel. And now you train another model which essentially look at the internal features of your main model, and is trained to detect a failure or what is called an out-of-distribution input, or something which is likely to be wrong. And then you can leverage that for many applications, including raising alerts in your driving systems. In this case, and you can, if you think in terms of even for end-to-end driving, the same philosophy or the same approach can be used to train an observer, which at some point for a specific input is going to say the decision of the system is going to be a failure, so you'd better take over. Another interesting and very challenging aspect of machine learning, in particular for safety critical systems, in particular driving systems, is their explainability. So again, it's a sort of common wisdom to say that neural networks and machine learning models are black boxes. It means essentially that they are very large and complex functions which have been trained from data with millions and now billions and now even hundreds of billions of parameters, and explaining what each parameter is doing for a given input in order to explain the output is essentially very difficult, if not possible at all. And one way to approach this sort of interpretability of a model is to build what are called counterfactual examples. So the idea is that it's the what-if question. So if I have a scene with like in this case, it's for a driving system, it looks at a scene through a camera and decides to move forward or to stop, etc. And you want to know, to understand why your system is taking certain decision. So the counterfactual explanation is to try modification, to find modification in your input scene, which are plausible, likely to happen in the real world, which are able to make the decision change. So in this case, you see on the left, it's a real scene, it's a real driving system saying it should stop. Now we have on the right, I'm not going to explain how we do that, by the way, maybe later. We have this slightly changed scene, which makes the system change the decision from stop to move forward. And if you look carefully, I'm not so sure you can see that yes, you can. There are the few differences are there. So here the braking lights of the cars are switched off to some extent, and the traffic lights go from red to green, which makes sense. So what it means is that the system has taken the original decision to stop for apparently good reasons, at least understandable reasons. So that's very important. So this is an early work we had last year at ECCV. The constraint we had is that we were only able to manipulate the scene without changing the layout, but only the sort of the texture or the color. That's why this example works fine with green to red or vice versa, or switching off the braking lights. But the flexibility we have is a bit limited. So in a more recent work that we are going to present in June at CVPR is extending the same idea, but now we can change the structure of the scene. So it's exactly the same thing, the same system. On the left, you have a real image. On the right, you see an image which has been manipulated automatically by the method in order to make sure that the autonomous driving system, which looks at this scene, decide to go from the decision of moving forward to the one of stopping. And again, here the interpretation is pretty clear. It has put the front car closer. So again, it's quite reassuring. The system is doing sensible things. Okay, so let's see. And in order to do that, yes, in order to do that, you need to manipulate a real scene. That's difficult. So we used, for that, we used this generative model from last year, which is called BlobGAN, which is able to generate scenes with some ability to manipulate the scene in terms of where are the objects, at which distance, which one is in front of the other one, etc. The main objective here in this type of work is to generate scenes, right? Now, the additional difficulty we have is that we want to use that in order to manipulate a real scene. So the system we put together goes as follows. We start from a real scene. We have a way, it's called inversion. We have a way to take this real scene and to turn it into one of these abstract, or not so abstract, but blob-based representation from this other work I just mentioned, which allows to some extent, to regenerate the same scene. So essentially, we have embedded the real scene into this representation space from which we know how to decode into a scene. And then we are going to manipulate this representation, move the blobs, etc. When I say we are going, it's just automatic, right? And you see the result. And then we decode or we generate the new manipulated scene. In this case, you see that many things have stayed the same, the layout, the trees, the road, but one vehicle now is closer. So this is how we did it. Some examples here. You see at the top the actual real scenes with the decision of the driving system, move forward or doesn't turn left, etc. And you see at the bottom how we flipped the decision by the manipulation of the scene. So first column, the object, the closest car is closer now, so it stops. Second example, it has somehow changed how busy is the road, so we can turn left. And on the right example, the car which is in front on the right is closer now and prevents the system from turning right. So again, it all makes sense. But this is qualitative analysis when we say it makes sense for the human. So we tried something difficult in this paper is how to quantitatively assess the power of these I'm going to skip that, of these counterfactual examples. To do that, we put together a small user experiment. And the idea here is that for some people, we showed them a number of these counterexamples, and we want to know whether it has helped them to understand how the driving system works. And to test that, then we asked these guys and other people who didn't get this to see whether they could predict the decision of the automatic system on new scenes. And this is what we got. So there is a very significant difference. This is the replication part of this table. It means that the people who have been sort of trained, it's a bit funny, we are training humans to understand the machine now, as opposed to the opposite. So for the people who have been trained using the counterfactual examples, they were way better at predicting the next decision of the system. And we did another thing, because these counterfactual explanations are here to understand the system, and in particular to detect biases which are not good. So what we did, we trained a bad driving system with a very strong biases that the user were not aware of. And we wanted to see, actually, the bias is as follows. The driving system couldn't turn right, well, was saying that it can turn right even if they had, how is it called? Yeah, so the turning right was also influenced by the fact that you have cars on the left, which is obviously wrong, so it was purposely put in the training of the driving system, and we wanted the people to detect or not, or to understand or not this bias, and it turns out, many of the people who were trained saw the bias, and not the other people at all. All right. For sake of time, I'm going to skip that and move directly to the takeaways. Anyway, the slides will be available. So, autonomous driving, assisted driving, etc. I think it's fair to say that it's a reality now, even if many people are not completely aware of that, it is a reality because of extremely important progress in terms of sensors, but also in terms of machine learning, obviously, and artificial intelligence, and also in terms of the hardware that we can put in the cars for the compute. And it goes from passenger cars, that I mentioned these new cars, I mentioned the Mercedes, it's also true for Honda, having level 3 systems on the highway, in traffic jams, but it goes all the way to very specific other, even niche markets, which are important. But I think probably some people were a bit optimistic when they were saying that it was around the corner to have autonomous driving cars everywhere in towns. So the challenges we have, we are still banging our heads, are related to all this data that we need, not only for training, but even worse, for testing our systems. So massive amount of data, usually annotated. This is not scalable. The current system, they are still lacking really reliability, explainability, and in order to be trusted completely. And the other thing which is important, not only for autonomous driving, but for all the high-risk systems with AI, at least in Europe, is that there is this new AI Act coming up, which might change the game, and we really have to be careful. Well, careful. We have to accompany that and to see how to be compliant. And this is for very good reason. And I will finish with new venues. I think because of also the price, the safety which is involved, etc., there is a lot to do in terms of training and validating all these systems, or part of them, virtually, meaning in simulation. So this is a very big trend that you see in the new mobility and autonomous mobility industry. I already mentioned self-supervised learning across modality, and I think it's just starting. So it's again how to leverage vast amount of unannotated data, whether it's actually driving data or not. And of course, related to that, there are now these incredible so-called foundation models, whether it's visual language models or even just language models, which are changing the face of AI at large, but in particular robotics. It was alluded to this morning, and also autonomous driving, in particular in order to do to recognize things without any training data. It's called zero shot, or to help with the annotation, to help with delivering explanation in text, or also to test things. And with that, I'm going to stop with this image just to see one way to use these models. This is from Midjourney. So you take a real scene, you ask to put a baby on this at this place, and you get this image. And you can easily imagine how these things can be useful for training and even better for testing our systems at scale automatically. So lots of exciting venues. And I will stop here with all the people in my team. And thank you for your attention and your patience in this world. Thank you.
So, time for questions. Thank you very much, Patrick, for exciting talk. Holger, please.
Mike is coming.
So thank you very much. That was super insightful. I hope you'll forgive me the question, but of course you're enthusiastic. I think you should be. To be perfectly honest, I would fully expect that at least you and I and most of the people in this room will live to see the day where autonomous driving level 5 becomes a reality, right? I really believe that this will happen. But let me ask you this. How long do you think we're really away from having level 4 without geofencing or even level 5 in European cities like Prague? In, let's say, more than just a few experimental cars, but in something that you and I can simply just, hop into. How long away would you think?
All the people who have answered this question in the past decade got it wrong. So I'm going to be a bit conservative here. I'm not sure it will happen in my lifetime for passenger cars. I wouldn't bet on that. I mean, we might be surprised. Things which have happened with natural language processing recently has also taken off guard in the other way some predictions. I think one of them, again, for really passenger cars not being geofenced, imagine that we have really solved all the reliability, the robustness, etc. One of the issues here is that it's not only about the autonomous system, it's about the other road users as well. So even if all the cars, they were autonomous, it's not only about cars. You have pedestrians, and hopefully the ratio even increases. So pedestrians, cyclists, etc. So, and in some big cities, the mixing is so dense and so packed. I think it's very difficult. Each day, so I walk to work in Paris. I look at the traffic with my Valeo.ai, and I think it's challenging. So I don't know. What I know for sure, what I believe more into the fact that in the coming years we will see for logistics and for robotic taxis and for shuttles, big time. Level 4 or 5 for passenger cars. I mean, we'll see, but I wouldn't. I mean, not in this decade, I don't think. But if you listen to some of the vocal people in the industry, not so much. Actually, if you listen to the car manufacturers, they have extremely toned down these announcements. As opposed to startups.
Except for Tesla, of course, right?
That's true. That's true. That's interesting, actually. Yes.
So we have actually on Slido we have someone asking to have more time for questions. So let's have a few more questions.
That's a good sign.
And there is a related question to this. Another way to think about the measure of performance of autonomous driving is to compare the autonomous car to people. And I think here the person is asking, well, is there, where we are in terms of, say, fatalities per kilometer? Like, are we getting, is the autonomous driving comparable, or when will it be comparable to, say, humans doing X fatalities per kilometers in the autonomous car?
That's a very difficult one. First of all, because to get the numbers at scale, you really need to get the reports from the people who are really deploying at scale. Actually, it's interesting to look at the Waymo safety report. Extremely good read. They communicate about the numbers, but even the way you compute the numbers is difficult because there are no metrics. And on top of that, obviously, if things go wrong, you disengage the system. So so what they measure is for nice, well, fortunately, it's not the number of fatalities which are caused by Cruise or Waymo. There are a few, I think. But what is the frequency of the disengagement compared to over the kilometers? But then you should know what are the type of kilometers that you have been driven. I mean, if you are doing that or in the Silicon Valley every day, the boring road there, I mean, it's maybe not representative in terms of statistics. So I would say, in a sense, it's way safer. I mean, than the human driver. I mean, it doesn't get drunk, doesn't fall asleep, etc. But I mean, getting a fair comparison. Another thing which is interesting is probably, well, this is interesting but difficult to do. Another thing which is interesting is to have the driving system in a shadow mode. So you are still driving as a human, and you see the system is doing. But of course, then the system is not accessing the closed loop of the driving, but at least you can compare things and record what is the driving of the human and what would be the driving of your system. And actually, you can even use that to train with the imitation learning and end-to-end driving systems. But so there are different ways to accommodate this, but it's difficult to assess the actual level of safety.
Yeah. Any more questions from the audience? Maybe let's ask one more.
What is the current level of automation of truck driving on highways in Europe or worldwide? Is there like some deployment of very autonomous trucks?
Well, I confess I don't have these numbers, but I mean I read a lot about even the media on these things, and I'm not aware of actual. The level of authorizations that we have already, I mentioned in San Francisco, for instance, for robotaxis. I'm not aware of any bold announcement about trucks being allowed, even experimentally. So it may be the case. I confess my lack of knowledge here, but the fact that it hasn't, I haven't heard about it is probably a sign that there is not much. There is, in the US in particular, there is a very visible and promising startup which is called Waabi, which has been started by Raquel Urtasun, which is focusing on that. So if it's probably one of the places to look at to have fresh news on the state of affairs for the trucks. There are other places, of course.
So maybe let's have one last question for Patrick, to take advantage of the expertise we have here from Peréz. Anyone? Any more questions? Holger, one more, please. Yes, please, one last question.
So I'm just curious whether you would share my assessment that long before we will ever have fully autonomous driving, we should have fully autonomous flying of commercial aircraft, right? First cargo and then passengers, because I would think that, you know, the way we do aviation is so much cleaner, so much more regulated, so much more technologically supported. So all these things that you said about the inner cities, all the nasty things that can happen to you, right? All the users of the space, that's really not such a big deal with airspace, right? Would you agree with that, or do you see this differently?
Actually, I was even about to say, isn't it already the case? I think a plane can do most of the stuff automatically, right? But of course, I agree. I'm not at all a specialist in aviation, but indeed, the domain of operation is so different. So there are many things that you don't have to care about at the same time. The way they have, I mean, the lifespan of a plane, it's much more than it's 50 years, right? And the design cycle is much longer. So even worse for space now, but for plane. So which means probably as well that you have some of the technologies which are quite ancient, they're quite old. So you know, probably they cannot enjoy the latest whatever GPU, etc. So they have their own challenges, and I think certification is definitely the harshest.
Okay, let's thank Patrick again for a wonderful presentation. Thank you, Patrick.